Welcome to Chemistry Grade 12 video lessons. I'm Mr. Harish Vaidiyangadil. This lesson we will be discussing about electrochemistry, lesson number 5.1, lesson title Voltaic Cell. Learning outcomes for the lesson: describe a way to obtain electrical energy from a redox reaction. Identify the parts of a voltaic cell and explain how each part operates. Well, calculate cell potential and determine the spontaneity of the redox reactions also. Keywords for the lesson: salt bridge, electrochemical cell, Voltaic cell, anode, cathode, reduction potential, standard hydrogen electrode. Let's see what does that mean by electrochemistry. Well, a camera captured this image of a mountain land. Camera traps are a non-invasive way to study animals by using a sensor that triggers a camera shutter when the animal approaches. Batteries power both the camera and the sensor. Chemical energy can be converted into electrical energy, and electrical energy can be converted into chemical energy. That is one of the main idea. You see here, the camera captures the animals that are moving around. Introduction: can you clap with one hand? No, you cannot. Likewise, voltaic cells have two half cells, and both are required to produce energy. Main idea: in voltaic cell, oxidation takes place at the anode, yield electrons that flow to the cathode, where reduction occurs. Redox in electrochemistry. Electrochemistry is the study of the redox process by which chemical energy is converted into electrical energy and vice versa. Let's see the oxidation which losing electron. Electron is lost by A, and reduction, that is gaining electrons. B gains electrons. A gets a positive charge and B gets a negative charge. A loses electron and B gains electrons. Losing electron oxidation whereas gaining electron reduction. Both together we call redox reaction if it takes place in one reaction. Apparatus that uses redox reaction to produce electrical energy we call electrochemical cells. Electrochemical cells will have two half cells in which one is oxidation and the one reduction takes place. Oxidation half cell, electron lost. Here in zinc becomes Zn2 plus 2 electrons. That electron is traveling through the external circuit and reaches on the other half cell where reduction occurs. Reduction is gaining of electrons. Here Cu2 plus, it gains electrons to become Cu. But still something is missing here. Bulb doesn't light up. What is missing here? The circuit is complete? No. Salt bridge were missing. A salt bridge is a pathway to allow the passage of ions from one side to another, so that ions do not build up around the electrode. Salt bridge helps to complete the circuit by helping to neutralize the charges. That will allow the ions to move through. See here, oxidation takes place in left hand half cell, where Zn is changing into Zn2 plus 2 electron, and the electron is moving through the external circuit and reaches to the next half cell where the copper Cu2 plus gains 2 electrons to become Cu. Here Zn2 plus becomes more, here Cu2 plus reduces. But to balance the charge we use a salt bridge. Salt bridge lets the ions to move through in that and balances or neutralizes the charges there. It will not support any mechanical mixing of the solution. simplest electrochemical cell is a Voltaic cell. There you will have zinc in Zn2 plus ion solution and copper in Cu2 plus ion solution. Electric charges can flow between 2 points when a difference in electric potential energy exists. A voltic cell is a type of electrochemical cell that converts chemical energy into electrical energy by a spontaneous redox reaction. What does it mean by spontaneous? See, a reaction one that occurs on its own without any energy input from the outside. We call it spontaneous reaction. See here, the energy conversion that occurs in voltic cell. Well, here always energy flows from a high potential to low potential. Here you can see potential energy will be high for the roller coaster on the top of the track. Whereas when it is on the bottom, it will have less potential energy while it will have the highest kinetic energy. You can see here kinetic energy will be high when it is moving through, potential energy will be high when it is on the high height or the high position. Similarly, an electrochemical cell has a potential energy to produce current because there is a difference in the ability of the electrodes to move electrons from the anode to the cathode. Electromotive force. EMF source supplying energy for moving charges. Always the electricity flows from the high potential to low potential. When the electrons or the charges comes to a battery, it will get boosted up and it will go with a faster speed. That's what the EMF source or a battery does. We have been hearing volt when it is connected with the electricity flow. Volt is a unit used to measure cell potential. The electric potential difference of a voltic cell is an indication of the energy that is available to move electrons from the anode to the cathode. If the voltage is higher, the movement will be faster. Let's watch a simple video regarding voltic cell. As you know here, it has got zinc in Zn2 plus ion solution and copper in copper 2 plus ion solution.
The spontaneous redox reaction between zinc metal and copper 2 ion can be harnessed in a voltaic cell to generate electricity. The cell consists of two half-cell compartments connected by an external circuit. Oxidation takes place in the anode compartment in which a zinc electrode dips into a zinc nitrate solution. Electrons leave this compartment, travel through the external circuit, and enter the cathode compartment. There, reduction takes place at a copper electrode dipping into a copper nitrate solution. A salt bridge maintains charge neutrality in the two compartments. Let's zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper-2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper-2 ions leave the solution and are reduced at the cathode. Thus, charge flows continually as the cell operates. Negative charge in the form of electrons flows from the anode through the external circuit to the cathode. As negative charge in the form of anions flows from the cathode compartment through the salt bridge to the anode compartment, positive charge in the form of cations flows in the opposite direction. The oxidation of zinc metal in the anode combines with the reduction of copper-2 ion in the cathode to give the overall cell reaction. Under standard conditions, this cell generates 1.10 volts of electricity.
Chemistry of voltaic cells. First of all, you have to understand half cells, the cell in which either oxidation or reduction takes place. We have used two half cells in voltaic cell. One is Zn in Zn2 plus aqueous solution, as well copper in Cu2 plus aqueous solution. One can act as anode. The electrode where oxidation takes place is called anode. You can remember it as an ox. As well, cathode, the electrode where reduction takes place is called cathode. You can remember it as a red cat. Let's find how to calculate the electrochemical cell potential. First of all, you have to know the tendency of a substance to gain electrons is its reduction potential. The reduction potential of an electrode cannot be determined directly because the reduction half reaction must be coupled with an oxidation half reaction. So, chemists decided to measure the reduction potential of all electrodes against one electrode, that is the standard hydrogen electrode, SHE. Let's see the parts of standard hydrogen electrode. Hydrogen gas will be bubbled through an inlet at 1 atm pressure, and a platinum electrode will be there, that is the inert electrode, and hydrogen gas, that is the gas which we have supplied, will be bubbling through, and 1 molar acid solution with 1 mole H plus aqueous will be there, and a salt bridge which connects the hydrogen half cell with the another half cell. If reduction takes place, the reaction will be 2H plus aqueous plus 2 electron gives H2. If oxidation takes place, H2 gas gives 2H plus aqueous plus 2 electron. Half cell potential. Half cell potential of any half cell can be measured by connecting it with standard hydrogen electrode. One of the half cell which we have used in the voltaic cell is copper in Cu2 plus aqueous solution. We can find out its cell potential by connecting it with standard hydrogen electrode. Standard hydrogen electrode will have a cell potential of 0 volt. So the electrode potential for copper when you're connecting with the standard hydrogen electrode is showing 0.3419 volt. It can be calculated by using the formula E standard cell is equal to E standard reduction minus E standard oxidation. E standard cell, that is being represented like this, and E standard reduction would be represented like this as well. E standard oxidation could be represented like this. When you connect Cu and Cu in Cu2 plus solution, that is one of the half cell in voltaic cell, when it's connecting with the standard hydrogen electrode, the reaction takes place. Cu2 plus 2 electron gives Cu, that is a reduction reaction. As well, the standard hydrogen electrode will undergo oxidation by changing H2 into 2H plus 2 electrons. The overall reaction for this one, the two electrons will get cancelled out and CH2 plus Cu2 plus aqueous gives 2H plus C solid. This reaction can be written in a form called cell notation. In the cell notation, you will have the reactant, how it is being changed into the product in the oxidation half cell, and there will be a salt bridge as well, reactant for the reduction half cell, that is Cu2 plus would changing into Cu as the product. A standard cell value would be plus 0.342 volt for copper in Cu2 plus. The other half cell which we have used in the Voltaic cell which we have discussed in the earlier, that is Zn2 plus. When you're connecting it with the standard hydrogen electrode, Zn changes into Zn2 plus 2 electron, that is oxidation half cell reaction. As well, hydrogen in the standard hydrogen electrode, 2H plus aqueous gains 2 electrons becomes H2 gas. The reduction reaction takes place there. Overall reaction, in this case also the electrons will get cancelled out and 2H plus aqueous plus Zn solid gives Zn2 plus aqueous plus H2 gas. This reaction also can be written as in the cell notation form. The reactant is Zn2 plus in the oxidation half cell, which is changing into Zn2 plus aqueous. Whereas in the reduction half cell, the reactant is hydrogen gas, which is changing into 2H plus aqueous. Its standard cell value is negative 0.764 volt. Negative sign indicates oxidation takes place. Well, when we are combining it, 0 volt is for standard hydrogen electrode. When you are connecting copper Cu2 plus with the standard hydrogen electrode, you have got plus 0.342 volt. The other half cell, when we are connected, it is minus 0.762 volt. Negative sign indicates the oxidation takes place, as well positive sign indicates reduction takes place. E standard cell value is equal to E standard reduction minus E standard oxidation. E standard reduction value you can see here, Cu2 plus to Cu, the value is 0.342 volt. Whereas for Zn2 plus the value is negative 0.762 volt. So the final answer is plus 1.104 volt. That is the standard electrode potential of the Voltaic cell which we have discussed. Now let's see some of the worked examples related to Voltaic cell. At the Voltaic cell, the following reduction half reaction represents the half cell of a Voltaic cell. Iodine solid plus 2 electron gives 2I minus aqueous, and Fe2 plus aqueous plus 2 electron gives Fe solid. Determine the overall cell reaction and the standard cell potential. Describe the cell using cell notation. Let's see. Analyze the problem first. Non-value. We have to know the equation. E standard cell is equal to E standard reduction minus E standard oxidation. Unknown. Overall cell reaction we have to find as well. E standard cell we have to find, and cell notations we have to do. Let's solve the problem. First of all, we have to write the equation and find the value from the data booklet, that is plus 0.536 volt for the reduction potential for iodine. As well for the iron, the reduction potential is negative 0.447 volt. Negative sign indicates the reaction is oxidation. Now E standard cell value is equal to E standard reduction minus E standard oxidation. E standard reduction is 0.536 minus negative 0.447. The value is plus 0.983 volt. Now let's write the equation in the correct way. Reduction half cell reaction takes place for iodine. I2 solid plus 2 electron gives 2I minus. As well, iron, the reaction has got reversed. Fe solid gives Fe2 plus 2 electron because oxidation half cell reaction. Now when you are cancelling the electrons, you will get I2 solid plus Fe solid gives 2I minus aqueous plus Fe2 plus aqueous. Cell notation can be iron Fe2 plus I2I minus. These two lines shows the salt bridge. When we are evaluating the answer, we have got the answer plus 938 volt, right? This is a positive, so the reaction is spontaneous. Let's summarize this session. Voltaic cell has got zinc electrode would be the for anode, as well anode oxidation reaction takes place, and anode will be negatively charged, whereas the voltaic cell which we have discussed has got copper electrode which is cathode, and it has got positive charge, and you have to remember it as red cat, meaning reduction at cathode. Standard potential of a voltaic cell is the difference between the standard reduction potential of the half cell reactions. Here, oxidation half cell would be the zinc Zn2 plus, and reduction half cell would be copper in copper 2 plus. Half cell, the standard potential is of the half cell can be measured by connecting it with standard hydrogen electrode. If the sign is positive, then it is reduction. If the sign is negative, it is oxidation. Standard hydrogen electrode is one of the half cell which is being used as the reference half cell, which has got hydrogen gas being bubbled at 1 atm by using platinum electrode being used there. A standard volt plus means 0 volt. Standard hydrogen electrode will have a 0 volt. Standard conditions 1 atm and 298 Kelvin, as well 1 mole per dm cube H plus ions would be there. In a half cell, either oxidation or reduction takes place. Anode is always the one with oxidation takes place. Cathode is the one with reduction takes place. Let's do some assessment. Here you can see Zn changes into Zn2 plus 2 electron. So this would be anode or cathode? It's anode. Anode oxidation takes place and it has got the negative charge. Let's see here. Cu2 plus changes into Cu. It's gaining 2 electrons. So that would be the answer here. It's cathode. Yes, reduction takes place. And it has got positive charge. And there is a connector between them, that is salt bridge. Let's see a few more assessment questions. The standard potential of a voltaic cell is the difference between the A. Standard reduction potential of the half cell reactions, B. Electrode voltage, C. Standard reduction potential of the cell and hydrogen, D. Half cell reactions and salt bridge. The answer is A. It's standard reduction potentials of the half cell reactions. The difference between the standard reduction potential of the two half cell reactions. Which of the following must be true of a salt bridge? A salt bridge must prevent the flow of charged particles. Ions can move through the salt bridge. The solutions joined by the salt bridge can mix freely. The tube of the salt bridge must remain open. The answer would be yes, it's B. Ions can move through the salt bridge. This is the end of the assessment and the session. Thank you very much.